There's a message woven into the fabric of the cosmos, a whisper so faint, it's traveled nearly 14 billion years to reach us. It's not a sound you can hear or a light you can see with your eyes, but it's there, humming quietly in the background of everything. This is the cosmic microwave background radiation, or CMB, and it's the oldest light in the universe. Think of it as the afterglow of the Big Bang, a snapshot frozen in time when the universe was just a newborn, barely 380,000 years old. But here's the astonishing part. This ancient light isn't just a relic. It's a treasure map hiding clues about how the universe was born, how it grew, and even how it might one day end. What if I told you that scientists can read this cosmic fingerprint like a detective deciphering a crime scene? Tiny fluctuations in this radiation, patterns no bigger than 1 part in 100,000, hold the blueprints for everything we see today. Galaxies, stars, even the vast cosmic web connecting them all, trace their origins back to these subtle ripples. And that's not all. The CMB has revealed secrets about dark energy, the mysterious force pushing the universe apart faster and faster, and dark matter, the invisible scaffolding holding it all together. These aren't just abstract ideas, they're the hidden forces shaping reality itself, and they're written into the light from the dawn of time. So how do we decode this celestial cipher? That's where the story gets even more fascinating. From groundbreaking telescopes like Planck and WMAP to daring balloon experiments above Antarctica, scientists have spent decades piecing together this cosmic puzzle. And what they've found is nothing short of revolutionary. The CMB doesn't just tell us where we came from, it hints at where we're headed. Could it reveal the ultimate fate of the universe? Could it uncover truths about dimensions beyond our own? Strap in, because we're about to take a journey through space and time, back to the very beginning, to uncover the secrets hidden in the oldest light there is. This isn't just a story about the past, it's a key to the future. To understand how this ancient light came to be, we have to rewind the cosmic clock to a time when the universe was unimaginably different. Picture a newborn cosmos, not filled with stars and galaxies, but a searing, opaque soup of particles so dense that light couldn't travel more than a tiny fraction of an inch before being absorbed again. For nearly 380,000 years, the universe was a swirling fog of plasma electrons and protons too energetic to form atoms, trapping photons in a relentless game of cosmic pinball. Then, in a pivotal moment, everything changed. As the universe expanded, it cooled just enough for electrons and protons to finally combine, forming the first neutral hydrogen atoms. Suddenly, light had an open road. Those trapped photons, once bouncing helplessly, burst free in every direction, creating the very first glow of the cosmos. That flash of liberation is what we now detect as the cosmic microwave background. It's not just light, it's the universe's first breath, a moment frozen in time. The most incredible part, everywhere you look in the sky, this radiation is almost perfectly uniform, like a quiet hum with only the tiniest variations, ripples that would one day become the seeds of galaxies. The discovery of this radiation in 1965 was equal parts luck and brilliance. Radio astronomers Arno Penzias and Robert Wilson were troubleshooting a persistent hiss in their antenna at Bell Labs, a noise that wouldn't go away no matter how many pigeons they shooed from the equipment. What they'd stumbled upon wasn't interference, it was the echo of creation itself, a whisper from the dawn of time. Their accidental breakthrough earned them a Nobel Prize and confirmed a bold prediction made years earlier. If the Big Bang was real, its afterglow should still be detectable. And there it was, a faint signal filling the entire sky, the ultimate validation that our universe had a fiery beginning. But the story doesn't end there. The CMB isn't just a relic, it's a time capsule. Those slight variations in temperature, some patches a fraction warmer, others cooler, tell us how matter began to clump together, setting the stage for everything that followed. Without those tiny imperfections, gravity wouldn't have had anything to work with, and the universe would have remained a featureless void. Instead, those ripples grew, pulling matter into the vast cosmic web we see today. So when you look up at the night sky, remember, the stars, the galaxies, even the emptiness between them, all trace back to those first faint whispers of light. Those faint temperature variations in the cosmic microwave background, so subtle they'd be imperceptible to human senses, are like the universe's first fingerprints. Imagine looking at a newborn's tiny hands and seeing not just delicate wrinkles, but the entire roadmap of their future, every growth spurt, every scar, every path they'll walk. That's what scientists are doing when they study these minute fluctuations. A patch of sky just slightly warmer here, a fraction cooler there. These differences of mere millionths of a degree tell an epic story of cosmic construction. What's astonishing is how these microscopic ripples became the scaffolding for everything we see. In the earliest moments, the universe was a nearly smooth sea of energy, but nearly is the key word. Quantum fluctuations, tiny, random variations at the smallest scales, left their mark, creating regions where matter was ever so slightly denser. Over billions of years, gravity amplified these differences, pulling more matter into the denser spots while emptying out the spaces between them. The warmer patches in the CMB, those were the future homes of galaxy clusters, the metropolises of the cosmos. The cooler spots, the seeds of vast cosmic voids, the universe's empty deserts. To map this blueprint, scientists use instruments so sensitive they could detect the heat of a snowflake from miles away. Space telescopes like Planck have scanned the entire sky, painstakingly measuring these temperature differences to create a cosmic baby picture with staggering detail. The resulting maps look almost like static on an old television, but to a cosmologist, they're as revealing as an architect's plans. By analyzing the size and distribution of these fluctuations, researchers can even determine the universe's recipe, how much ordinary matter, dark matter, and dark energy it contains. It's like tasting a spoonful of soup and knowing exactly how much salt, pepper, and spice went into the pot 14 billion years ago. One of the most profound revelations from these maps is how perfectly they match predictions. The patterns align with theories of cosmic inflation, the idea that the universe underwent an exponential growth spurt in its first fraction of a second. Those quantum wrinkles got stretched across the cosmos, becoming the large-scale structures we see today. Without inflation, the CMB would look far smoother, and galaxies might never have formed at all. It's as if the universe left us a carefully coded message. Here's how I began, here's how I grew, and here's what I'm made of. But the CMB isn't just a history book, it's also a measuring tape. By studying how these ripples bend and shift as they travel across the universe, scientists can trace the invisible scaffolding of dark matter and measure the accelerating push of dark energy. It's like watching shadows move across a wall to deduce the shape of objects you can't see. Every new observation peels back another layer, revealing deeper mysteries about the forces that shaped our cosmic home. And as technology advances, who knows what other secrets we'll uncover in this ancient light? The universe's first whisper might still have stories left to tell. The early universe wasn't just a silent expanse, it was a roaring concert, a cosmic symphony playing out in the searing heat of primordial plasma. Sound waves, massive and powerful, rippled through this dense, seething sea of particles, compressing and rarefying matter like the pulsing beats of some celestial drum. These weren't ordinary sound waves, though. They were Baryon acoustic oscillations, pressure waves traveling at nearly half the speed of light, sculpting the universe in ways we're only now beginning to decode. And just like echoes in a canyon, their faint signatures are frozen into the cosmic microwave background, waiting to be read. Picture this: a single ripple moving outward from an overdense region, pushing matter ahead of it like a snowplow, while gravity pulls material back toward the center. The result, a spherical shell of slightly denser matter, a footprint roughly 500 million light-years across. These shells became the universe's scaffolding, the invisible framework on which galaxies would later cling. When we look at the CMB, we're seeing the moment those waves froze in place, the instant the universe cooled enough for atoms to form, locking those oscillations into the fabric of space like grooves in a cosmic record. What's truly mind-blowing is how precise these imprints are. By measuring the scale of these frozen waves like a tailor measuring the spacing between stitches, scientists can determine the universe's expansion rate with astonishing accuracy. It's as if the early universe handed us a ruler calibrated to its own dimensions, allowing us to measure not just how fast it's growing, but what it's made of. Dark matter, that mysterious substance that outweighs visible matter 5-to-1, reveals its presence by how it bends these acoustic peaks. Dark energy, the force accelerating cosmic expansion, leaves its mark by subtly stretching the pattern over time. The implications are staggering. These sound waves don't just tell us about the past, they're a key to the present and future. By comparing the ancient oscillations in the CMB to their modern counterparts in galaxy surveys, astronomers have uncovered a cosmic tug-of-war, the relentless push of dark energy against gravity's pull. Without these primordial echoes, we'd be deaf to the universe's deepest rhythms, blind to the forces shaping its destiny. So the next time you hear a distant echo, remember, the cosmos has been singing its story for billions of years, and we're finally learning how to listen. Dark matter may be invisible, but its fingerprints are all over the cosmic microwave background. Think of it like this: if the universe were a grand orchestra, dark matter would be the unseen conductor, guiding every movement with its gravitational pull. While we can't see it directly, its influence is written into the CMB's faint temperature variations, a ghostly signature that reveals just how much of the cosmos it dominates. Here's how it works. In those first chaotic moments after the Big Bang, dark matter didn't just sit idly by. Unlike ordinary matter, which interacts with light and gets buffeted by radiation pressure, dark matter's particles barely noticed the cosmic storm raging around them. They simply clumped together under gravity's pull, creating dense pockets that acted like gravitational anchors. These invisible wells of mass tugged at the surrounding plasma, shaping the distribution of matter in ways that would later freeze into the CMB's subtle ripples. Without dark matter's steadying hand, those ripples would have been weaker, smoother, too faint to ever birth the galaxies we see today. The numbers are staggering. By meticulously measuring the size and spacing of these fluctuations, scientists have calculated that dark matter makes up roughly 27% of the universe's total content. To put that in perspective, all the stars, planets, gas, and dust, everything we can see or touch accounts for less than 5%. Dark matter isn't just a minor player, it's the cosmic scaffolding that holds the universe together. One of the most compelling pieces of evidence comes from comparing the CMB with modern galaxy surveys. The patterns match almost perfectly, like two halves of a broken seal snapped back into place. The CMB shows us where dark matter's gravitational wells first formed, and today's galaxy maps reveal how those same regions grew into the vast clusters and filaments we observe now. It's as if we're watching a time-lapse of the universe's construction, with dark matter as the invisible foreman directing every beam and column. But here's the twist: despite knowing how much dark matter exists and how it behaves, we still don't know what it actually is. Is it a sea of undiscovered particles, remnants from the universe's fiery birth, or something even stranger, bending the rules of physics as we know them? The CMB can't answer that directly, but it has ruled out countless theories, narrowing the search like a cosmic sieve. Every new observation peels back another layer, bringing us closer to solving one of science's greatest mysteries. So the next time you gaze up at the night sky, remember, the stars and galaxies are only the visible crumbs of a much larger feast. The real story is written in the darkness between them, in the whispers of ancient light that still carry echoes of the universe's hidden architect. And thanks to the cosmic microwave background, we're finally learning how to read the blueprint. If dark matter is the unseen architect of the cosmos, dark energy is the phantom force tearing its blueprints apart. Here's the staggering truth hidden in the cosmic microwave background. The universe isn't just expanding, it's accelerating, stretching faster and faster, as if some invisible hand is pressing down on the cosmic gas pedal. This isn't just a curiosity, it's a revolution in our understanding of reality. The CMB's subtle patterns, combined with observations of distant supernova, reveal that roughly 68% of the universe's energy is locked into this mysterious repulsive force we call dark energy. Picture a balloon inflating at an ever-increasing speed, each dot on its surface racing away from the others, not just because the balloon grows, but because the rubber itself seems to gain some strange anti-gravity property. That's the effect dark energy has on space-time. While gravity tries to pull galaxies together, dark energy pushes them apart, and over billions of years, it's winning the tug of war. The CMB captures the opening act of this cosmic drama, the moment when dark energy was just a whisper in the universe's infancy, its presence barely detectable amid the denser, hotter early cosmos. How do we know dark energy exists if we can't see it? The clues are etched into the CMB's temperature fluctuations like cracks in drying paint. By measuring the precise spacing of these ripples, the same Baryon acoustic oscillations that shaped galaxy clusters, scientists can calculate how the universe's expansion rate has changed over time. The results are mind-bending. For the first 9 billion years, gravity dominated, slowing the expansion. But around 5 billion years ago, dark energy took over and the cosmos began accelerating. It's as if the universe itself hit puberty and suddenly decided to sprint instead of walk. The real shock came when researchers compared CMB data with observations of Type Ia supernova, stellar explosions so uniform they're called standard candles. These cosmic beacons revealed that distant supernovae were dimmer than expected, meaning space had stretched more than predicted during their light's journey to us. The conclusion was inescapable. Something was counteracting gravity's pull on a cosmic scale. The CMB provided the missing piece, showing how dark energy's influence grew as the universe expanded and matter thinned out. Together, these two lines of evidence painted the same startling picture: our universe is flying apart, and no one knows why. What makes dark energy so baffling is how little we understand it. The leading theory suggests it's the energy of empty space itself, a property Einstein once called the cosmological constant before dismissing it as his greatest blunder. Yet the CMB's fingerprints suggest this energy isn't constant at all. It may have fluctuated over cosmic history, or even interacted with dark matter in ways we're only beginning to probe. Some theories propose entirely new physics, extra dimensions, evolving fields, or even a breakdown of Einstein's gravity on the largest scales. One thing's certain: dark energy holds the keys to the universe's ultimate fate. If it continues to accelerate expansion unchecked, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future civilizations with a sky nearly empty of stars. The CMB gives us a front-row seat to this unfolding mystery, a time-lapse of cosmic evolution written in microwaves. Every new observation peels back another layer, revealing just how much we still have to learn about the invisible force shaping our cosmic destiny. The universe's oldest light isn't just a relic, it's a roadmap to the unknown. The universe's first moments weren't a gentle awakening, they were a violent, exponential explosion of space itself. In less time than it takes light to cross a single atom, the cosmos ballooned from smaller than a proton to nearly the size of a grapefruit, stretching quantum fluctuations into cosmic-scale wrinkles that would one day become galaxies. This mind-bending growth spurt, known as cosmic inflation, isn't just a wild theory, it's the only explanation that fits the cosmic microwave background's near-perfect uniformity and its faint, telltale imperfections. Imagine blowing up a balloon covered in microscopic dots. As it inflates, two dots that were once neighbors end up far apart, yet the pattern remains evenly spread. That's what inflation did to the early universe. Before this hyper-expansion, every particle was close enough to interact, smoothing out temperature differences like a cosmic thermostat. Then inflation stretched these regions light-years apart, so quickly that light couldn't keep up, locking in that uniformity before the Big Bang's afterglow even began. That's why the CMB's temperature is identical in opposite corners of the sky, despite those regions never having time to communicate under normal physics. But here's where it gets even more fascinating. Inflation didn't just stretch space, it magnified quantum jitters, those tiny random fluctuations at the smallest scales. What were once subatomic ripples became the seeds for all cosmic structure. The CMB's temperature variations, those millionth of a degree differences, are essentially quantum mechanics writ large, blown up to cosmic proportions. Without inflation's rapid expansion, those fluctuations would have been too weak for gravity to sculpt galaxies. The universe would have remained a featureless void, cold and empty. The evidence doesn't stop there. Inflation predicts a specific pattern in the CMB's polarization, a subtle swirly imprint called B-modes, created by gravitational waves rippling through spacetime during that explosive growth. While these signals are incredibly faint, experiments like BICEP and the South Pole Telescope are hunting for them like cosmic archaeologists brushing dust off a fossil. Finding them would be like discovering the universe's birth certificate, signed in gravitational waves. Critics once argued inflation was untestable, a just-so story for the cosmos. But the CMB's precise measurements have turned it into a predictive powerhouse. The theory forecasted the exact statistical distribution of those temperature fluctuations, and when Planck's space telescope mapped them with unprecedented precision, the match was uncanny. It's as if the universe left us a puzzle where every piece fits only one way, and inflation is the key to assembling it. Yet mysteries remain. What triggered inflation? What stopped it? Some theories suggest it wasn't a one-time event but part of a multiverse, where countless bubble universes pop into existence endlessly. Others propose exotic fields or higher dimensional physics. The CMB can't answer these questions directly, but it's narrowed the possibilities, ruling out entire classes of theories. Every new generation of telescopes peels back another layer, bringing us closer to understanding how everything from quarks to quasars traces back to that unimaginable burst of expansion in the universe's first fleeting moments. The beauty of inflation is how elegantly it solves cosmic riddles while posing profound new ones. It turns the CMB from a static snapshot into a dynamic story, a chapter in the universe's autobiography where space itself stretched faster than light, transforming quantum whispers into the galaxies we call home. And somewhere in that ancient light, there may still be clues waiting to reveal what happened in the very first tick of the cosmic clock. The fate of the universe isn't written in the stars, it's encoded in the cosmic microwave background's geometry. Scientists call this the cosmic triangle, a delicate balance between ordinary matter, and dark energy that determines whether our cosmos will end in fire, ice, or eternal expansion. The CMB acts like a cosmic scale, measuring the universe's total density with such precision that it can tell us whether space is curved like a sphere, saddle-shaped, or perfectly flat, a distinction that holds the key to everything that lies ahead. Here's how it works. Imagine space itself as a vast sheet of rubber. Place 3 laser pointers billions of light years apart and measure the angles between their beams. In a closed universe with enough matter to eventually recollapse, those angles would add up to more than 180 degrees, like drawing a triangle on a balloon. An open universe destined to expand forever into emptiness would produce angles summing to less than 180 degrees, like carving lines on a saddle. But the CMB reveals something extraordinary. Our universe is razor-edge flat, with angles precisely matching Euclidean geometry. This Goldilocks scenario means the cosmos contains just enough mass and energy to balance on the knife edge between collapse and endless dispersal. Dark energy tips these cosmic scales, while matter, both visible and dark, tries to pull the universe back together. Dark energy pushes it apart with increasing force. The CMB's temperature fluctuations let scientists calculate this tug-of-war's exact parameters, revealing that dark energy accounts for nearly 70% of the universe's total content. That's why distant galaxies aren't just receding, they're accelerating away from us, their light redshifted into oblivion by expanding space itself. If this continues, the cosmos will face a big freeze, where galaxies vanish beyond an unreachable horizon, leaving future civilizations staring into an empty, lightless void. Yet the CMB hints at even stranger possibilities. Some theories suggest dark energy's strength might change over time, potentially leading to a big rip where even atoms are torn apart, or a big crunch if the repulsive force weakens and gravity regains dominance. The Planck satellite's detailed maps show these scenarios are unlikely, but not impossible. Like a detective reconstructing a crime scene from minute traces of evidence, cosmologists use the CMB's subtle patterns to test these apocalyptic hypotheses against cold, hard data. What's truly humbling is how much hangs in the balance. A few percent more matter, and the universe would have collapsed billions of years ago. A fraction less dark energy, and gravity might still be slowing expansion instead of losing ground. That we exist in this precise moment, able to decode these cosmic clues, is a testament to how finely tuned, or astonishingly improbable, our universe's parameters really are. The CMB doesn't just show us where we came from. It's a crystal ball revealing possibilities we're only beginning to comprehend. And as new telescopes probe even deeper, we may yet find twists in this cosmic tale that rewrite everything we thought we knew about tomorrow. The Planck satellite didn't just observe the cosmic microwave background, it transformed it into a high-definition masterpiece. Launched in 2009 by the European Space Agency, this technological marvel spent 4.5 years scanning the sky with sensitivity so sharp it could detect temperature variations as small as 1 part in a million. The result, the most detailed baby picture of the universe ever taken, a map so precise it refined the cosmos's age down to a razor-thin margin, 13.8 billion years, give or take just 37 million. That's like measuring the lifespan of an ancient oak tree to within a single day. But Planck's revelations went far beyond mere cosmic accounting. Its data peeled back layers of the universe's composition with surgical precision, confirming that ordinary matter, the stuff of stars, planets, and us, makes up a paltry 4.9% of everything. Dark matter, that mysterious gravitational glue, accounts for 26.8%, while dark energy, the enigmatic force accelerating cosmic expansion, dominates at 68.3%. These numbers might seem dry, but they're the universe's recipe, and Planck measured each ingredient to the nearest decimal. The real shock came when scientists scrutinized Planck's maps for anomalies, tiny deviations from the expected patterns. One glaring oddity, a mysterious cold spot spanning 1 billion light-years in the southern sky, a region so unusually chill it defies standard cosmological explanations. Some theorists speculated it could be evidence of a collision with another universe during inflation, a cosmic bruise left by a long-ago encounter with a parallel reality. Others propose it's a supervoid, a vast emptiness stretching spacetime like a rubber sheet. But here's the twist: no known void is large enough to produce such an effect. The cold spot remains an unsolved riddle, a crack in the foundation of our cosmic understanding. Then there's the curious case of the axis of evil, a whimsical name for a spine-tingling discovery. The CMB's fluctuations aren't perfectly random. They show faint alignments across the sky, as if the universe has a preferred direction. This violates a sacred tenet of cosmology called the Copernican principle, which states that no place or direction in space should be special. If confirmed, it could mean our universe isn't as uniform as we thought, or worse, that Planck inadvertently glimpsed the fingerprint of something beyond our cosmos, like a gravitational tug from another dimension. Planck's legacy isn't just about answers, it's about questions that redefine the frontiers of physics. Its data ruled out entire classes of inflationary models while leaving others hanging by a thread. It measured the universe's expansion rate with such precision that it inadvertently sparked a crisis, disagreeing with measurements from nearby galaxies by enough to suggest we might be missing a crucial piece of the cosmic puzzle. Some call it tension, others whisper the word revolution. What makes Planck's maps so extraordinary isn't just their detail, but their humility. They remind us that every time we think we've got the universe figured out, it tosses us a curveball. Those anomalies might be statistical flukes, or they might be the first tremors of a paradigm shift, clues that the cosmos is far stranger than we ever imagined. As we stare into Planck's intricate tapestry of microwaves, one thing becomes clear: the universe's oldest light still has secrets to spill, and the next chapter of this cosmic detective story is waiting to be written. The cosmic microwave background is supposed to be the universe's most predictable relic, a nearly uniform glow with tiny, random fluctuations. But when scientists stared deep into Planck's ultra-precise maps, they found something unsettling. The CMB isn't perfectly random. Its fluctuations show strange alignments across the sky, as if the cosmos has a hidden axis. Astronomers call this the axis of evil, a playful name for a discovery that challenges everything we thought we knew about cosmic structure. Picture throwing a handful of confetti into the air, only to watch it arrange itself into neat parallel lines instead of scattering randomly. That's essentially what the CMB appears to do. Across vast swaths of sky, temperature variations seem to align along a particular direction, violating one of cosmology's most sacred principles, that the universe should look the same in all directions. This isn't just a minor oddity, it's a potential crack in the foundation of modern physics. If the universe has a preferred axis, it means our place in space might be special after all, upending centuries of Copernican thinking that insisted Earth, and by extension, humanity, holds no privileged position. Theories attempting to explain this anomaly range from the mundane to the mind-bending. On the conservative end, some researchers argue it's simply a statistical fluke, a cosmic mirage that will vanish with more precise measurements. Others suggest our galaxy's motion through space might be distorting the CMB's patterns, like wind bending the image in a funhouse mirror. But the most tantalizing explanations venture into uncharted territory. Could the axis of evil be evidence of a multiverse, a gravitational tug from a neighboring bubble universe imprinting itself on our sky? Or does it hint at exotic physics, a primordial magnetic field frozen into space-time, or even relics from a time before the Big Bang? One particularly provocative idea involves cosmic textures, defects in space-time structure left over from the universe's fiery birth. These hypothetical knots in the fabric of reality could create observable imprints, much like wrinkles in a sheet of paper alter how light passes through it. If such textures exist, they'd warp the CMB in precisely the way we're observing. The challenge: no one's ever detected a cosmic texture before, and their existence would require rewriting parts of quantum field theory. Then there's the cold spot, another glaring irregularity in the CMB's otherwise smooth tapestry. Stretching over 1 billion light years, this unusually frigid patch defies standard explanations. Some models suggest it's a supervoid, a vast emptiness where matter is unusually sparse. But here's the catch: the largest known voids are still too small to produce such a dramatic temperature drop. Alternative explanations border on science fiction. Could it be a collision between our universe and another during inflation, like two soap bubbles brushing in some higher dimensional foam? The idea isn't as far-fetched as it sounds. Certain string theory models predict exactly this kind of multiversal interaction. What makes these anomalies so electrifying is their potential to rewrite physics. Most cosmological discoveries confirm existing theories. These do the opposite. They poke holes in our understanding, suggesting that something fundamental is missing from the standard model of cosmology. It's like discovering your supposedly random wallpaper pattern actually contains hidden Morse code. Once you see it, you can't unsee it. Yet skepticism remains healthy. Extraordinary claims require extraordinary evidence, and no single anomaly has yet risen to that level. The cold spot could be a statistical outlier. The axis of evil might vanish with better data, but with each new generation of telescopes like the upcoming Lightbird mission designed to study CMB polarization with unprecedented precision, we edge closer to answers. These cosmic irregularities might be glitches in our measurements, or they might be the first tremors of a scientific revolution. Either way, they prove one thing: even in its oldest light, the universe still knows how to surprise us. The cosmic microwave background isn't just a faint glow, it's a twisted tapestry of light, its waves subtly polarized by the universe's most violent and transformative moments. This polarization, a directional twisting of light waves, is like the universe's own fingerprint, encoding secrets far beyond temperature alone. While the CMB's heat map tells us where matter clumped together, its polarization reveals how that matter moved, offering a front-row seat to the cosmic drama that unfolded in the first trillionth of a second after the Big Bang. At the heart of this story are two distinct patterns scientists call E modes and B modes. E modes are the gentle swirls created when light scatters off electrons in the early universe, tracing the distribution of matter like ripples on a pond. But it's the B modes that have cosmologists holding their breath, a fainter, curl-like signal that could carry the imprint of primordial gravitational waves. These aren't ordinary waves. They're space-time itself vibrating from the universe's explosive birth during cosmic inflation, stretching and squeezing the fabric of reality as they propagated outward. Detecting them would be like finding the tremors from the Big Bang's first heartbeat. The challenge? These signals are absurdly faint. The B-mode polarization from inflation is buried under a mountain of noise, including interference from dust in our own galaxy and gravitational lensing from later cosmic structures. It's like trying to hear a whisper in a hurricane. That's where projects like the Simons Observatory come in, a next-generation array of telescopes perched high in Chile's Atacama Desert, where thin, dry air offers a crystal-clear view of the cosmos. With tens of thousands of detectors scanning the sky, it's designed to tease out these elusive signals with sensitivity 100 times greater than previous experiments. What makes this hunt so electrifying is what's at stake. If B modes are found, they'd provide the first direct evidence of cosmic inflation, confirming that the universe underwent exponential expansion in its first fleeting moments. The strength of these signals could even reveal the energy scale at which inflation occurred, offering clues about the unification of quantum mechanics and gravity, a realm currently beyond the reach of particle accelerators. It's as if the universe left us a cosmic Rosetta Stone, written not in hieroglyphs but in the subtle twists of ancient light. Yet there's a twist. Some theories suggest inflation might not be the only way to produce primordial B modes. Alternative models like bouncing cosmologies or cyclic universes make their own predictions. The absence of B modes could be just as revolutionary as their discovery, forcing us to reconsider the Big Bang's fiery narrative. Either way, the CMB's polarization isn't just a new chapter in cosmology. It's a whole new language waiting to be deciphered. And as telescopes grow more sensitive, we might soon read the universe's earliest diary entries, scribbled in the warped light of creation itself. Gravitational waves are often called the universe's loudest whispers, ripples in spacetime itself, sent crashing through the cosmos by the most violent events imaginable. Black holes colliding, neutron stars merging, even the Big Bang's birth pangs. But the most elusive of these waves aren't from recent cataclysms. They're fossils, imprinted onto the cosmic microwave background during the universe's first unimaginable fraction of a second. If detected, these primordial gravitational waves would be our direct line to inflation's explosive moment, a smoking gun proving space once expanded faster than light itself. Here's why this matters. During cosmic inflation, quantum fluctuations weren't the only things getting stretched to cosmic proportions. Spacetime itself was vibrating violently, generating gravitational waves with wavelengths that inflation bloated to astronomical scales. These waves interacted with the primordial plasma, subtly twisting the light that would eventually become the CMB in a distinctive curl-like pattern called B-mode polarization. It's as if the universe's fabric was plucked like a guitar string, leaving its vibrations frozen into the afterglow light. Finding this pattern would be like discovering the Big Bang's original soundtrack, a recording of spacetime's first tremors. The hunt for these signals is pushing technology to its limits. Ground-based experiments like BICEP and the South Pole Telescope scan the sky from Earth's driest deserts, where atmospheric interference is minimal. Space missions like Lightbird, scheduled for launch in the late 2020s, will avoid Earth's interference entirely, mapping the CMB's polarization with unprecedented precision. The challenge: these inflationary B modes are buried under layers of noise, later distortions from galactic dust, gravitational lensing, even the polarization patterns created by ordinary matter's motion in the early universe. Separating the primordial signal from these contaminants is like trying to isolate a single violin's note in a symphony played at hurricane volume. What makes this search so thrilling are the stakes. The strength of these B modes, measured by a parameter called the tensor-to-scalar ratio, could reveal inflation's energy scale, a strong signal would suggest inflation occurred at energies approaching the Planck scale, where quantum mechanics and gravity merge. This would bridge particle physics with cosmology, offering clues about quantum gravity and perhaps even string theory. A null result, while initially disappointing, could be equally revolutionary, forcing us to consider alternatives to inflation like bouncing cosmologies or cyclic universes. Already, the universe has dropped tantalizing hints. In 2014, the BICEP2 team announced they detected B modes at a level suggesting an energy scale just below the Planck energy. The celebration was short-lived. Further analysis showed galactic dust could explain most of the signal, but the episode proved something vital. We're now sensitive enough to brush against these primordial whispers. Next-generation telescopes will peer even deeper, potentially crossing the threshold where detection becomes undeniable. Imagine the implications. Confirming primordial gravitational waves wouldn't just validate inflation, it would open a new observational window on the universe's first moments, a period forever hidden from traditional telescopes. These waves carry pristine information, unaffected by the plasma and chaos that scrambled other signals from the early cosmos. They could reveal whether inflation was driven by a single quantum field or a more complex interaction, perhaps even hinting at extra dimensions. The CMB's polarization isn't just light, it's a time capsule waiting to share secrets from the dawn of everything. And with every technological leap, we inch closer to cracking it open. The idea of a multiverse isn't just science fiction, it's a serious scientific hypothesis, and the cosmic microwave background might be hiding the first clues. Picture this, our universe as one bubble in a vast cosmic foam, each bubble with its own unique laws of physics, its own history, even its own dimensions. While we can't peek into these other universes directly, some cosmologists believe their gravitational influence could leave faint marks on our CMB, like fingerprints on a window pane. Take that infamous cold spot, for instance, a billion light-year-wide region of the sky where the CMB is noticeably cooler than it should be. One provocative explanation. It's a cosmic bruise, a relic from a long-ago collision with another universe during inflation. Think of it like two soap bubbles bumping in a sink. Where they touched, energy transferred, leaving a subtle imprint. If true, this cold spot wouldn't just be an anomaly, it'd be our first glimpse beyond the edge of reality as we know it. The math behind this is mind-bending. In certain multiverse models, when two bubble universes collide, the interaction creates a disturbance in spacetime that propagates outward, distorting the CMB in predictable ways. These distortions wouldn't look like random noise, they'd form distinct circular or disk-like patterns, edges where the physics of one universe brushed against another. Scientists have even scoured Planck's data for these telltale shapes, hunting for irregularities that can't be explained by standard cosmology. So far, no smoking gun, but the search is far from over. Skeptics argue these anomalies could just be statistical flukes or artifacts of galactic interference. After all, extraordinary claims require extraordinary evidence, and a single cold spot isn't enough to rewrite physics. But here's what's fascinating. Even if the multiverse hypothesis remains unproven, the CMB is forcing us to ask bigger questions. Why is our universe so finely tuned for life? If there are infinite universes with different physical constants, ours might just be the lucky one where stars, planets, and thinkers like us could emerge. The real test will come with next-generation telescopes. Projects like the Cosmic Microwave Background Stage 4 experiment aim to map the CMB's polarization with such precision that even the faintest multiversal fingerprints couldn't hide. Whether they find proof or not, the pursuit is changing how we see our place in the cosmos. The CMB isn't just a snapshot of our universe's infancy, it might be the first page of a much, much larger story. At the smallest scales imaginable, where reality flickers in and out of existence, quantum fluctuations once danced in the primordial chaos of the early universe. These weren't just random blips, they were the universe's first brushstrokes, tiny variations in energy that would one day sculpt galaxies, stars, and the vast cosmic web. When inflation stretched spacetime exponentially, it didn't just smooth the cosmos, it magnified these quantum whispers, transforming subatomic ripples into the seeds of everything we see today. The cosmic microwave background captures this moment like a photograph, freezing those fluctuations into a pattern of slightly warmer and cooler patches, a quantum fingerprint written across the sky. What's astonishing is how delicate this process was. Those initial quantum jitters were unimaginably small variations of just one part in 100,000. To put that in perspective, if the early universe had been as smooth as a mirror, these fluctuations would have been no larger than a single grain of sand on an entire beach. Yet over billions of years, gravity amplified these tiny imperfections, pulling matter into denser regions while emptying out the spaces between them. The slightly warmer spots in the CMB, those were the future homes of superclusters where galaxies would one day gather in dazzling metropolises, the cooler patches. The blueprints for cosmic voids, the universe's empty deserts. This isn't just theoretical, it's etched into the CMB's geometry. Scientists can measure the exact distribution of these fluctuations, and what they've found is nothing short of miraculous. The patterns match predictions from quantum field theory with eerie precision, as if the universe itself followed a recipe written at the smallest scales. It's like finding a fossilized raindrop and realizing its ripples perfectly match the contours of today's continents. The CMB doesn't just show us where structure came from, it reveals how quantum physics, operating in a realm a billion times smaller than an atom, became the architect of the cosmos. But here's where it gets even stranger. These quantum fluctuations weren't just random noise, they followed a very specific statistical pattern called a Gaussian distribution. Imagine rolling a die an infinite number of times. Most results cluster around the average, with extreme outliers becoming exponentially rare. That's exactly what we see in the CMB's temperature variations. This statistical fingerprint is a smoking gun for their quantum origin, as only processes at those scales produce such perfect randomness. If the fluctuations had come from some classical process like turbulence in the early universe, their distribution would look entirely different. The implications are staggering. It means the galaxies around us, the stars we see at night, even the planets that might harbor life, all owe their existence to quantum uncertainty, to the universe's inherent unpredictability at the smallest scales. Without these fluctuations, gravity would have had nothing to work with, and the cosmos would have remained a featureless void. The CMB is more than a relic. It's a bridge between the quantum and the cosmic, a reminder that the universe's grandest structures were born from its smallest tremors. Yet mysteries linger. Why did these fluctuations have exactly the right amplitude to produce a universe like ours? Some theories suggest inflation's energy scale set their strength too weak, and no galaxies would form, too strong, and matter would have clumped into black holes. Others propose even wilder ideas, like quantum fluctuations interacting with hidden fields or extra dimensions. Whatever the answer, the CMB remains our most direct window into that quantum dawn, a snapshot of the moment randomness became structure and the universe began writing its own story. Every particle of matter in our universe has a mirror image, a twin made of antimatter, identical in every way except for an opposite charge. When matter and antimatter meet, they annihilate in a flash of pure energy. According to the laws of physics, the Big Bang should have created equal amounts of both, leaving behind nothing but light. Yet here we are, surrounded by galaxies, stars, and planets made entirely of matter. This cosmic contradiction, known as Baryon asymmetry, is one of the deepest puzzles in modern physics, and the cosmic microwave background holds vital clues to solving it. Hidden within the CMB's subtle temperature variations is evidence of this ancient imbalance. The patterns of hot and cold spots reveal how much ordinary matter, protons, neutrons, and electrons, exists in the cosmos compared to radiation. The numbers don't lie. For every billion photons in the CMB, there's only about one baryon, one lone survivor of a near-total annihilation that should have left nothing behind. That tiny excess, that 1 in a billion advantage, is why we exist at all. The mystery deepens when we consider how precise this imbalance had to be. If matter had outnumbered antimatter by even a slightly smaller fraction, the universe would have been too sparse for galaxies to form. Too much, and dense black holes would dominate. Somehow, nature struck a perfect balance, and the CMB lets us measure that balance with astonishing precision. But how did it happen? One leading theory points to conditions in the early universe that violated the supposed symmetry between matter and antimatter. In 1967, physicist Andrei Sakharov identified 3 crucial ingredients needed for this imbalance, a process that treats matter and antimatter differently, a departure from thermal equilibrium, and interactions that don't conserve baryon number. Certain particle physics models, like those involving neutrinos or grand unified theories, could provide these conditions, but definitive proof remains elusive. The CMB offers a unique testing ground. If baryon asymmetry arose from particle interactions in the universe's first moments, those events would have left imprints in the CMB's polarization patterns. Experiments hunting for these subtle signatures could narrow down the possibilities, potentially pinpointing which exotic particles or forces tipped the scales in matter's favor. What's at stake isn't just academic. If antimatter had won, even by the slimmest margin, reality as we know it would have vanished before it began. The CMB doesn't just remind us of how close we came to nothingness, it's a challenge to uncover the hidden physics that made our existence possible. And until we solve it, the universe's greatest magic trick remains unexplained. How something emerged from almost nothing, leaving behind a world where matter, against all odds, got the last laugh. Neutrinos are the universe's quietest ghost particles, so elusive they can pass through a light year of lead without a single collision. Born in the nuclear furnaces of stars and the cataclysms of supernova, these nearly massless wanderers flooded the early cosmos, outnumbering atoms by billions to one. And when the cosmic microwave background was born, neutrinos left their fingerprints all over it, subtly shaping the universe's first light in ways we're only now learning to decode. Here's how they did it. In the universe's first few seconds, neutrinos were anything but shy. They raced through the dense, searing plasma at nearly the speed of light, their sheer energy helping to smooth out the primordial soup. But as the cosmos expanded and cooled, these particles became cosmic drifters, barely interacting with matter yet still influencing its destiny. Their presence created a unique signature in the CMB's temperature fluctuations, a slight smoothing effect on certain scales, like a gentle hand pressing down on the universe's wrinkles. What's astonishing is what this tells us about neutrinos' mass. For decades, physicists assumed these particles were completely weightless, but the CMB's patterns reveal otherwise. By measuring how neutrino free streaming dampened acoustic oscillations in the early plasma, scientists have pinned down their combined mass to a razor-thin sliver, less than 1 electron volt, or a billionth the mass of a single proton. That might sound insignificant, but across trillions of neutrinos, it adds up to a gravitational influence that helped sculpt the cosmic web we see today. The implications are staggering. Neutrinos may be feather-light, but their abundance means they played a crucial role in how matter clumped together. Without their subtle push, galaxies might have formed earlier and in denser clusters, rewriting the entire story of cosmic evolution. The CMB lets us measure this influence with precision, acting as a time capsule of neutrino behavior during the universe's most formative era. But the mystery deepens when we consider what we still don't know. Why are neutrinos so impossibly light compared to other particles? Could there be a sterile neutrino, an even more elusive variant that evades detection entirely? The CMB's data hints at tantalizing gaps in our understanding, discrepancies that might point to new physics beyond the standard model. Experiments like the upcoming CMB S4 project aim to probe these questions with unprecedented sensitivity, potentially rewriting the rules of particle physics using the oldest light in the universe. What's truly humbling is realizing how much of the cosmos is shaped by the invisible. Neutrinos, once thought to be mere cosmic background noise, turn out to be key players in the universe's grand design. And as we refine our measurements, we're not just studying these ghostly particles, we're uncovering the subtle forces that quietly guided everything from the first stars to the galaxies we call home. The CMB isn't just a snapshot of the past. It's a neutrino detector written in microwaves, revealing secrets even the most advanced labs on Earth can't touch. Black holes aren't just the universe's ultimate cosmic vacuum cleaners, they might also be its oldest relics. While we usually picture black holes as monstrous giants, born from collapsing stars or galactic mergers, some theories suggest they could have formed in the very first moments after the Big Bang, when the universe was a seething cauldron of unimaginable density. These primordial black holes, some no larger than an atom but packing the mass of a mountain, could still be lurking in the cosmos today. And if they exist, their fingerprints might be hiding in the cosmic microwave background, etched into the oldest light we can see. Think of the early universe as a bubbling pot of space-time itself. In those chaotic first seconds, quantum fluctuations could have created pockets so dense they collapsed directly into black holes no star death required. Some might have evaporated instantly thanks to Hawking radiation, while others, with just the right mass, could have survived for billions of years. These ancient survivors would be invisible, drifting through space like cosmic ghosts, but their presence could solve two of astronomy's biggest puzzles: the nature of dark matter and the missing links in our understanding of gravity. Here's where the CMB comes in. If primordial black holes were numerous enough, their gravity would have subtly warped space-time, bending the paths of photons as they traveled through the early universe. This distortion would leave faint but detectable imprints in the CMB's polarization, patterns, twists, and turns that can't be explained by ordinary matter alone. Scientists have scoured Planck's data for these anomalies, hunting for telltale signs of black holes that might have formed before the first stars ever flickered to life. The implications are staggering. If even a fraction of dark matter is made up of these primordial black holes, it would rewrite the story of cosmic structure. Unlike hypothetical dark matter particles, black holes would have clumped together differently in the early universe, altering how galaxies formed and how the cosmic web took shape. The CMB's fluctuations could reveal these differences, acting like a cosmic scale that weighs the invisible. But the hunt isn't just about dark matter. Primordial black holes could also be the key to understanding quantum gravity, the holy grail of modern physics. Their formation would depend on conditions so extreme that they straddle the line between quantum mechanics and general relativity, two theories that famously refuse to play nice. Detecting them in the CMB wouldn't just confirm their existence, it could offer a glimpse into the laws that govern the universe at energies no particle collider will ever reach. Of course, not all theorists are convinced. Some argue that the lack of observed gravitational lensing events where a black hole's gravity bends light from background stars rules out primordial black holes as a major dark matter candidate. Others point to the CMB's near-perfect Gaussian fluctuations, which seem to leave little room for the dramatic distortions black holes would create. But science thrives on mystery, and the possibility remains tantalizing. Next-generation telescopes, like the upcoming Nancy Grace Roman Space Telescope, could settle the debate. With unprecedented sensitivity, they'll scan the skies for the fleeting shadows of black holes passing in front of distant stars, while future CMB experiments probe even deeper into the polarization patterns that might betray their presence. Whether these primordial monsters are out there or not, the search itself is pushing the boundaries of cosmology, forcing us to ask deeper questions about how the universe began and what might still be hiding in its oldest light. The cosmic microwave background seems to tell two contradictory stories about life in the universe. On one hand, its near-perfect uniformity suggests a cosmos where habitable conditions are vanishingly rare, a vast, cold expanse where Earth might be a lonely oasis. The CMB's smoothness implies that matter was distributed with such precision that even slight variations could have left the universe too chaotic or too empty for life to take root. Yet those same tiny fluctuations, those 1 part in 100,000 ripples, also reveal something astonishing. Without them, galaxies, stars, and planets might never have formed at all. The very imperfections that make the universe uneven also made it fertile. This paradox forces us to confront a profound question. Is life an inevitable outcome of cosmic structure or a statistical fluke? The CMB's patterns suggest both possibilities. Regions where matter clumped slightly denser became gravitational wells, pulling in gas to form stars and planets. Cooler, emptier patches evolved into voids, the cosmic deserts separating islands of habitability. By mapping these fluctuations, we're essentially charting the universe's potential for life, not just where it could exist, but how common or rare those conditions might be. Take the so-called Goldilocks principle to cosmic scales. For life as we know it to emerge, a planet needs liquid water, stable orbits, and the right mix of elements, all factors tied to the universe's initial density variations. Too much clustering and stellar systems would be torn apart by gravitational chaos. Too little, and matter might never coalesce into planets at all. The CMB reveals that our universe walked this tightrope with astonishing precision. Its fluctuations fine-tuned enough to allow complexity, but not so extreme as to prevent it. But here's where the story takes a speculative turn. While the CMB shows life-friendly conditions exist, it doesn't tell us how often they lead to living, thinking beings. Some theorists argue that in a multiverse where countless universes bubble into existence with different physical constants, ours is simply one where the numbers worked out. Others see the CMB's delicate balance as evidence of something deeper, a fundamental principle that favors complexity. Either way, this ancient light forces us to reckon with our place in the cosmos. Are we a cosmic accident or part of a grander pattern? The search for extraterrestrial intelligence adds another layer. If life emerges readily, the CMB's vast tapestry of galaxies should be teeming with it. Yet the eerie silence of the universe, the fact that we've found no signs of alien civilizations, might hint otherwise. This Fermi paradox finds an unexpected mirror in the CMB's contradictions. Just as its smoothness and fluctuations tell dual stories, the cosmos might be both perfectly suited for life and strangely empty of it. future CMB experiments could sharpen this picture. By measuring polarization patterns with greater precision, we might identify regions where matter clustered in ways particularly favorable to life-bearing planets. Some models even suggest that certain statistical anomalies in the CMB could correlate with pockets of the universe where physical constants vary slightly, regions where life might take forms beyond our imagination. Ultimately, the CMB doesn't answer whether we're alone, but it frames the question in a way nothing else can. Those faint microwaves aren't just a relic of the past, they're a mirror, reflecting both the unlikeliness of our existence and the tantalizing possibility that somewhere in the cosmic dark, other lights have flickered on. Whether those lights are distant stars or distant minds remains the greatest mystery of all. Time's arrow points in one direction forward, and the cosmic microwave background holds the secret to why. That faint glow filling the sky isn't just ancient light. It's the universe's original wound-up clock, set in motion when the cosmos was a seething, ultra-dense furnace. The CMB's extraordinary smoothness at the Big Bang represents an incredibly low entropy state, like a perfectly stacked deck of cards before the shuffle. This improbable order is what makes time's one-way street possible, creating the irreversible flow from past to future that we experience every moment. Think of entropy as nature's accountant, always tallying the universe's tendency toward disorder. When you stir cream into coffee, it naturally mixes, never unmixes, because high entropy states are overwhelmingly more likely. The early universe defied this expectation. The CMB reveals a cosmos that began in a bizarrely organized state, with matter and energy distributed with near-perfect uniformity. This low entropy was the winding of the cosmic spring, and everything since, stars igniting, galaxies spinning, life evolving, has been that spring unwinding, driving the universe toward the chaotic equilibrium we call heat death. Here's the twist: without the CMB's pristine initial conditions, time as we know it wouldn't exist. The arrow of time isn't just about clocks ticking, it's about causality itself. We remember the past because entropy was lower then, leaving orderly traces like footprints in sand. The future, by contrast, is a fog of increasing disorder where footprints vanish. The CMB's photons, streaming toward us from the universe's infancy, are those first footprints, fossilized evidence of a moment when everything was poised to unravel. This raises a profound mystery. Why did the universe start with such unnaturally low entropy? Some theorists suggest it's a clue to deeper physics, like quantum gravity or a multiverse where our cosmos is one orderly bubble in a froth of chaos. Others see it as pure anthropic selection. Only in a universe with time's arrow could observers like us arise to ponder it. Whatever the explanation, the CMB's cold glow is more than a relic. It's the ticking heart of time itself, the pulse that lets us distinguish yesterday from tomorrow. And as its photons continue to redshift into oblivion, they carry with them the irreversible march of cosmic change, a reminder that even the universe is bound by time's unyielding arrow. The cosmic microwave background won't shine forever. Right now, its faint glow is already stretched from visible light into microwaves, a relic fading with every passing second as the universe relentlessly expands. But in trillions of years, this ancient light will face a far more dramatic fate. Redshifted into complete undetectability, its photons stretched so thin they'll dissolve into the cold, dark background of space itself. The CMB, our most direct link to the Big Bang, will vanish from observational reach, leaving any future civilizations blind to the universe's fiery birth. Imagine a distant future where astronomers peer into the sky with technology far beyond ours, searching for clues to cosmic origins. Instead of finding the CMB's telltale glow, they'll confront an empty void, a sky stripped of its oldest light. Without this cosmic Rosetta Stone, the very idea of a Big Bang might become unimaginable. The expansion of space, the existence of dark energy, even the concept of an evolving universe could fade into myth, replaced by theories untethered from the evidence we take for granted today. This isn't just speculation, it's inevitable physics. As space stretches, the CMB's photons lose energy, their wavelengths growing longer until they're indistinguishable from the random noise of the cosmos. What's now a crisp microwave signal at 2.7 degrees above absolute zero will cool to a millionth of a degree, then a billionth, fading into oblivion like an ember swallowed by the night. The universe's first light will have burned out, leaving no trace behind. Yet there's a profound irony here. The same force that makes the CMB detectable, the expansion of space, is also its eventual executioner. Today, we live in a golden age of cosmology, where the afterglow of creation is still bright enough to map in exquisite detail. Future eras won't be so lucky. By the time the Milky Way merges with Andromeda in 4 billion years, the CMB will already be 20% fainter. In 100 billion years, it'll be redshifted into radio waves so weak that only the most advanced civilizations could hope to detect it. And in a trillion silence, what's startling is how much we'd lose without this light. The CMB isn't just a historical artifact, it's the foundation of modern cosmology. Without it, we'd have no proof of the universe's age, no way to measure dark energy's grip on cosmic expansion, no window into the quantum seeds that grew into galaxies. Future astronomers might never deduce that space itself is stretching, let alone that it began in a fiery burst. The universe's autobiography would lose its first chapter, leaving later generations to guess at origins they can no longer see. This raises a haunting question: how many cosmic secrets have already faded beyond recovery? If the CMB's disappearance is inevitable, what other clues to the universe's nature might vanish before we ever detect them? We're living in a privileged sliver of time, sandwiched between the Big Bang's afterglow and the coming darkness, a brief window when the cosmos still whispers its secrets to those who know how to listen. The CMB's impending fade isn't just a curiosity, it's a countdown reminding us that some truths are only visible for a cosmic moment, and once they're gone, they might be lost forever. The cosmic microwave background isn't some static artifact of the past, it's a living frontier, and the next generation of telescopes is about to crack it wide open. Imagine instruments so sensitive they could detect the heat left by a snowflake in deep space, then multiply that precision 1,000-fold. That's the promise of projects like CMB S4, a global array of next-generation telescopes designed to scrutinize the CMB's faintest whispers with resolution we can barely fathom today. These aren't just incremental upgrades, they're quantum leaps capable of spotting distortions 100 times fainter than what current technology can see. What makes this new era so electrifying is how it transforms the CMB from a snapshot into a dynamic laboratory. Take inflation, for instance, the theory that the universe underwent exponential expansion in its first split second. While current data supports the idea, CMB S4 could hunt for the specific type of gravitational waves inflation would have produced, encoded in the CMB's polarization like grooves on a cosmic record. Finding them wouldn't just confirm inflation, it would reveal the energy scale at which it occurred, offering clues about the unification of all fundamental forces. It's like discovering not just that a bomb went off, but exactly what kind of explosive was used. Dark energy's secrets are equally within reach. By mapping how the CMB's ancient ripples align with today's galaxy clusters, these telescopes could measure dark energy's equation of state, a parameter telling us whether its repulsive force is constant or changing over time. If it's varying, that could mean dark energy isn't Einstein's cosmological constant after all, but something far stranger, a dynamic field evolving alongside the cosmos, or even evidence of extra dimensions leaking gravity into our universe. The implications would rewrite textbooks overnight. Then there's the hunt for anomalies, those cosmic wrinkles that don't fit the standard model. The infamous cold spot, the axis of evil, and other statistical oddities might finally get explanations. Perhaps they're signs of a multiversal collision, relics from a pre-Big Bang phase, or evidence of exotic particles long since vanished. With CMB S4's resolution, we'll either confirm these as flukes or unlock doors to physics beyond our wildest theories. But here's the most thrilling part, the discoveries we can't yet predict. Every time humanity has built a more powerful telescope, we've stumbled upon the unimaginable black holes, dark matter, accelerating expansion. The CMB's next chapter will likely be no different. As these instruments come online in the late 2020s, they won't just test existing ideas, they'll reveal cosmic truths we haven't even thought to question. The universe's oldest light still has stories left to tell, and we're just learning how to listen. The cosmic microwave background has sparked wild theories, from claims it holds alien messages to arguments it disproves the Big Bang entirely. Let's set the record straight. The CMB isn't a cosmic Rorschach test open to interpretation. It's one of the most rigorously measured phenomena in science, scrutinized by satellites, ground-based telescopes, and supercomputers running countless simulations. Those who claim it contradicts the Big Bang often misunderstand a key point. The CMB's near-perfect uniformity doesn't mean the universe lacked a fiery beginning. It's the smoking gun that proves one. Inflation theory predicted this smoothness, explaining how regions now billions of light-years apart were once in contact before space expanded faster than light could keep up. Then there's the myth of hidden messages, the idea that advanced civilizations encoded signals in the CMB's temperature fluctuations. While it makes for gripping sci-fi, the reality is far more fascinating. Those patterns aren't artificial. They're quantum fingerprints stretched to cosmic scales, the universe's natural handwriting. No statistical analysis has ever found non-random structures beyond what physics predicts. What some call anomalies are usually just the limitations of our instruments or the cosmic variance we'd expect in any finite dataset. When the Planck satellite mapped the CMB with millionth of a degree precision, it didn't reveal cryptic symbols, it confirmed quantum mechanics on the grandest stage imaginable. Another persistent misconception is that the CMB's temperature proves the universe was once uniformly hot everywhere. In truth, the temperature we measure isn't heat in the traditional sense. It's the afterglow of a moment when the universe became transparent, a snapshot of photons finally free to travel after being trapped in plasma. The slight variations we see aren't errors in the data, they're the seeds of all cosmic structure. Without those tiny imperfections, gravity would have had nothing to amplify, and galaxies, including our own, might never have formed. Perhaps the most dangerous myth is that the CMB's mysteries undermine mainstream cosmology. In reality, every anomaly from the cold spot to the axis of evil has driven science forward, not shattered it. True, some features challenge our expectations, but that's how progress works. Dark matter was once an ad hoc explanation. Now it's the cornerstone of cosmic structure. The CMB doesn't hide conspiracy or catastrophe. It invites curiosity, pushing us to dig deeper, build better telescopes, and refine our theories. At its core, the CMB is a triumph of human ingenuity. It's not a canvas for fantasies, but a mirror reflecting our growing understanding of the cosmos. Every wild theory it inspires only highlights how extraordinary the truth really is. that we can trace the universe's history back to its first light, using nothing but microwaves and math. The real magic isn't in imagined codes or controversies, it's in the fact that we've decoded the universe's birth certificate at all. For thousands of years, humans have looked up at the night sky and asked the same fundamental questions. Where did all this come from? Are we alone? What does it mean? The cosmic microwave background represents the culmination of that ancient curiosity, a direct line to answers our ancestors could only dream of. Picture Babylonian astronomers etching celestial patterns into clay tablets, or Mayan priests aligning temples with Venus's path. These early stargazers mapped what they could see, but the CMB gives us something far more profound, a way to observe what's invisible, to hear the universe's origin story in its own voice. This journey from naked eye observations to precision cosmology reads like humanity's greatest adventure. When Galileo first pointed his telescope at Jupiter's moons in 1610, he shattered the idea that Earth was the universe's center. When Edwin Hubble discovered galaxies beyond the Milky Way in 1924, he revealed a cosmos vaster than anyone imagined, but decoding the CMB. That's like finding the Rosetta Stone of existence itself, a cipher that translates quantum whispers into galactic structures. Where ancient cultures saw mythic patterns in the stars, we now read the literal blueprints of reality in microwaves. What makes this modern quest so extraordinary isn't just the technology, it's the collaboration across generations and cultures. The CMB's discovery in 1965 was accidental, but its interpretation required insights from across physics, quantum theory to explain its fluctuations, general relativity to model its expansion, even thermodynamics to understand its perfect thermal spectrum. Today, researchers from dozens of countries work together on experiments like the Atacama Cosmology Telescope or the South Pole Telescope, braving extreme environments to capture this ancient light with ever greater precision. Science has become humanity's shared language, and the CMB is our universal text. Yet for all our progress, the most humbling realization might be how much we still don't know. The same CMB that confirmed the Big Bang also revealed that 95% of the universe's content, dark matter and dark energy, remains mysterious. In a beautiful irony, our greatest cosmic map has shown us how little we've charted. This isn't failure, it's invitation. Every anomaly, every unanswered question is a torch passed to future generations, just as Galileo passed his telescope to Newton and Newton's laws to Einstein. Standing between ancient stargazers and tomorrow's cosmologists, we're privileged to witness a pivotal moment. For the first time in history, we can test theories about the universe's birth with real data, not just philosophy. The CMB connects us to civilizations passed through shared wonder while offering tools they never had, a chance to not just speculate about creation, but to measure it. In its faint glow, we find both our cosmic insignificance and our extraordinary potential, the story of the universe written in light, waiting to be read. You don't need a billion-dollar satellite to eavesdrop on the universe's oldest light, just a backyard radio telescope, some open-source software, and a dash of cosmic curiosity. While professional astronomers chase groundbreaking discoveries with instruments like Planck, a growing community of amateur scientists and citizen cosmologists are making their own contributions to decoding the CMB. Thanks to publicly available datasets from space missions and radio astronomy kits, the secrets of the Big Bang's afterglow aren't locked away in ivory towers anymore. They're hiding in plain sight, waiting for anyone with a laptop and an internet connection to uncover them. Take the Planck Legacy Archive, for example. This treasure trove of raw CMB data, the same information used by Nobel Prize-winning researchers, is completely free to access. With tools like Python libraries for astrophysics or even beginner-friendly platforms like Google's Colab notebooks, enthusiasts can recreate iconic cosmic maps from scratch. Imagine filtering through noise patterns to reveal the same temperature fluctuations that hint at dark energy's grip on the universe, or stitching together microwave frequency bands to see how the CMB looks across different wavelengths. It's like being handed the keys to a time machine, one that lets you peer back to the universe's infancy using the same tools as the pros. For those who crave hands-on experimentation, building a basic CMB detector is surprisingly within reach. While you won't replicate Planck's precision in your garage, projects like the Cosmic Microwave Background Dipole Antenna demonstrate the principles behind professional observatories. Using a modified satellite dish, a low-noise amplifier, and a software-defined radio dongle, hobbyists can detect the CMB's dipole anisotropy, the subtle blue shift and redshift caused by Earth's motion through space. It's the same phenomenon that told astronomers our galaxy isn't stationary but hurtling through the cosmos at over 1 million miles per hour. Catching that signal yourself isn't just educational, it's a visceral connection to the universe's grand motion. The beauty of amateur CMB exploration lies in its collaborative spirit. Online forums like the Radio Astronomy group on cloudy nights buzz with stories of kitchen table breakthroughs, from high school students reprocessing WMAP data to find anomalies, to retired engineers building horn antennas tuned to 3 GHz, the sweet spot for CMB observations. Some even contribute to real science through platforms like Zooniverse, where volunteers help classify unusual features in cosmic microwave maps that algorithms might miss. In 2018, a German amateur astronomer spotted a peculiar alignment in Planck's polarization data that sparked fresh discussions about inflationary models. While it wasn't a paradigm-shifting discovery, it proved that passionate outsiders can still nudge cosmology forward. What's most inspiring about this grassroots movement is how it demystifies the universe. When you tweak a homemade radiometer to filter out terrestrial interference and finally isolate the CMB's signature hum, a whisper from 14 billion years ago, cosmology stops being abstract. It becomes something you've touched, measured, and questioned yourself. Whether you're sifting through public datasets or soldering circuits under a desk lamp, you're participating in humanity's oldest quest to understand where we came from. And in that process, the universe's grandest mysteries become not just concepts in a textbook, but signals waiting in the static, inviting anyone bold enough to listen. The cosmic microwave background does more than map the universe's infancy. It holds up a mirror to our deepest existential questions. That faint glow filling the night sky isn't just radiation. It's a philosophical puzzle box, challenging everything we assume about reality, time, and our fragile place in the cosmos. Consider this: every photon in the CMB has traveled nearly 14 billion years to reach us, making it the ultimate time capsule. But here's the twist: when we observe it, we're not just looking back in time, we're confronting the unsettling truth that much of the universe is fundamentally unknowable. The CMB marks the edge of our observable horizon, the limit beyond which light hasn't had time to reach us since the Big Bang. What lies beyond? Infinite space. Parallel universes, or just more of the same, stretching endlessly into the dark? The CMB doesn't answer these questions, it taunts us with them. This ancient light also reshapes how we think about time itself. The CMB's near-perfect uniformity suggests that causality, the idea that causes precede effects, operated differently in the universe's first moments. regions now separated by tens of billions of light years were once close enough to exchange information, their temperatures balancing like coffee and cream left to stir. But inflation stretched these regions apart faster than light could bridge the gap, freezing their uniformity in place. This isn't just physics, it's a challenge to our linear intuition. The early universe behaved like a magic trick, revealing connections that defy our everyday experience of time and distance. Then there's the haunting question of fine-tuning. The CMB reveals a cosmos balanced on a knife's edge. Those tiny temperature fluctuations were just strong enough to seed galaxies, but not so extreme that matter collapsed into black holes. If gravity had been slightly stronger or dark energy weaker, the universe might never have grown complex enough for stars, planets, or thinkers like us to exist. This precision fuels debates about whether our universe is a statistical fluke in a multiverse, or if some deeper principle, a law of nature we haven't discovered yet, guarantees life-friendly conditions. The CMB doesn't settle this debate, but it forces us to wrestle with it, transforming cosmology from a study of distant objects into a meditation on why anything exists at all. Perhaps most humbling is how the CMB redefines human significance. In a cosmos where galaxies number in the trillions, each containing billions of stars, Earth is less than a speck of dust in a hurricane. Yet here we are, decoding the universe's birth certificate from microwave particles that began their journey before our planet, our sun, even atoms themselves existed. There's poetry in that, a species fleeting by cosmic standards, grasping at truth spanning eternity. The CMB reminds us that we're both inconsequential and extraordinary, a brief flicker of consciousness in an ancient sea of light, daring to ask questions that the universe itself seems designed to provoke. This duality of wonder and insignificance is the CMB's greatest gift to philosophy. It shows us a cosmos vast enough to dwarf our egos, yet ordered enough to be understood. Whether that's coincidence or destiny, the answer remains written in microwaves, waiting for the next curious mind to listen. Like uncovering fragments of an ancient civilization, scientists meticulously study the cosmic microwave background not just as light, but as layered strata of cosmic history. Each subtle variation in temperature, those millionth of a degree differences, acts like a geological formation, preserving events from different epochs of the universe's evolution. The warmest patches trace back to regions where matter was denser in the primordial soup, destined to become galaxy clusters. The cooler spots, they're the cosmic equivalent of air pockets in sedimentary rock, marking voids where gravity lost the battle against expansion. This cosmic archaeology reveals something remarkable. The CMB isn't a single snapshot but a palimpsest, a document overwritten by eons of cosmic activity. Just as archaeologists use carbon dating to pinpoint the age of artifacts, cosmologists measure the CMB's acoustic peaks, the frozen echoes of sound waves that rippled through the early universe. The spacing between these peaks acts like a cosmic ruler, calibrated to measure the universe's expansion history with precision no terrestrial instrument could match. It's like finding a buried city where every brick is stamped with its exact date of creation, allowing us to reconstruct timelines stretching back to the first microsecond. But the real treasure lies in the anomalies, the cosmic equivalents of unexpected pottery shards or misplaced fossils. Take the cold spot, that billion light-year-wide chill in the CMB's otherwise uniform glow. Some theorize it's the imprint of a supervoid so vast it defies conventional models, while others whisper about collisions with parallel universes. Then there's the mysterious scarcity of large-scale fluctuations. Why does the universe lack mountains where matter clumped more dramatically than inflation predicts? These quirks aren't flaws in the data, They're puzzles begging for new physics, like an archaeologist stumbling upon a tool that predates known civilization. The tools of this cosmic dig are as sophisticated as any space-age trowel or ground-penetrating radar. Telescopes like the Atacama Cosmology Telescope don't just capture images, they perform spectral analysis on ancient light, teasing apart polarization patterns like scholars deciphering faded ink. Supercomputers then simulate millions of possible universes, comparing their virtual CMBs to our observed one, a process akin to reconstructing broken pottery by testing every possible fragment combination. The result, a three-dimensional timeline of cosmic evolution, from the plasma haze of the Big Bang to the intricate web of galaxies we see today. What's astonishing is how much this celestial excavation has rewritten our cosmic narrative. Before the CMB, theories about the universe's infancy were largely speculative philosophical musings with little observational grounding. Now, we can trace the universe's growth spurts like rings in a tree trunk, pinpointing when dark energy began dominating gravity's pull or when the first stars flickered to life. The CMB doesn't just tell us where we came from, it reveals how we fit into a story still being written, one where every new observation is another layer carefully brushed aside, bringing us closer to the universe's deepest secrets. Hollywood loves a good cosmic mystery, and the cosmic microwave background has played the role of ultimate enigma more times than you might think. Remember that spine-tingling moment in Contact when Jodie Foster's character, Ellie Arroway, tunes her radio telescope into the hiss of the CMB, only to discover a hidden message encoded within it. The film took creative liberties, but it tapped into something real, the CMB's uncanny ability to spark our imagination. That static isn't just noise, it's the universe's oldest soundtrack, and storytellers can't resist weaving it into narratives about first contact, hidden truths, and the nature of existence itself. The Big Bang Theory took a lighter approach, turning the CMB into a punchline for Sheldon's relentless pedantry. In one episode, he corrects a child's science fair project about the afterglow of creation, insisting it's technically the cosmic microwave background radiation. It's comedy, but it reflects how deeply this scientific milestone has seeped into mainstream culture. Even the X-Files couldn't resist. An episode titled Biogenesis suggested the CMB contained a message from extraterrestrials, blending real science with Mulder's signature conspiracy theories. What's fascinating is how these fictional portrayals mirror humanity's real fascination with the CMB. The idea that the universe might be hiding a message, whether from aliens, a higher power, or the fabric of reality itself, isn't just sci-fi fodder. It's a modern echo of ancient sky myths where celestial patterns held divine secrets. The CMB's faint whisper invites us to project our hopes and fears onto it, transforming cold physics into a canvas for storytelling. But here's the twist: the real CMB is more awe-inspiring than any Hollywood script. Unlike fictional portrayals of perfect alien codes, the actual fluctuations are messy, random, and profoundly beautiful in their natural imperfection. They don't spell out a message, but they do tell a story, one about quantum jitters stretched across the cosmos, about invisible dark matter shaping galaxies, about a universe that's stranger than any screenwriter could invent. Even video games have gotten in on the action. In Destiny 2, the CMB becomes a key plot device, with characters calling it the First Light and linking it to the game's mysterious cosmic forces. It's a testament to how this scientific discovery has transcended labs and textbooks to become a cultural touchstone, a symbol of humanity's quest to decode the unknown. The CMB's pop culture fame reveals something deeper. Science and storytelling aren't so different. Both seek to explain where we came from. Both thrive on mystery. And both remind us that the universe's greatest wonders don't need embellishment. They just need us to listen closely to the static and to wonder what secrets it might still hold. The hunt to decode the cosmic microwave background isn't confined to any single lab or nation. It's a planetary mission with telescopes perched on icy deserts, high-altitude plateaus, and even orbiting Earth itself. Take the South Pole Telescope, a marvel of engineering buried under Antarctica's eternal night. Here, in the coldest, driest place on Earth, scientists brave temperatures plunging below -100 degrees Fahrenheit to capture the CMB's faint whispers. The pole's thin, stable atmosphere and months-long darkness make it perfect for observing microwaves without interference, turning this frozen wasteland into one of cosmology's most valuable real estates. But this isn't just an American endeavor. Researchers from over a dozen countries, from Norway to Japan, collaborate here, sharing data and insights as if national borders didn't exist. Meanwhile, high in Chile's Atacama Desert, another extreme environment chosen for its bone-dry air, the Simons Observatory hums with activity. This international partnership combines the brainpower of universities from the US, Canada, the UK, and beyond, all focused on mapping the CMB's polarization with unprecedented precision. The Atacama's altitude, over 16,000 feet above sea level, places it above much of Earth's water vapor, giving telescopes here a crystal-clear view of the ancient light. Local Chilean engineers work side by side with global teams, blending regional expertise with cutting-edge technology. It's a microcosm of how CMB research transcends politics, creating a rare space where collaboration trumps competition. Then there are the space missions where cooperation reaches interstellar levels. The European Space Agency's Planck satellite, launched in 2009, involved scientists from over 40 nations, all contributing instruments, algorithms, and analysis. Planck's all-sky maps didn't just belong to Europe, they were immediately shared with researchers worldwide, fueling discoveries from Beijing to Berkeley. Similarly, NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, partnered with universities across 5 continents to refine the universe's age and composition. These projects aren't just about hardware, they're about pooling humanity's collective curiosity, proving that the cosmos speaks a universal language. What's striking is how these collaborations tackle challenges too vast for any one country to solve alone. Building a CMB telescope requires materials science from Germany, cryogenics from Japan, data processing from India, and logistical support from local communities near each site. When the BICEP and Keck arrays detected potential signs of primordial gravitational waves in 2014, it took researchers from 8 countries to verify and ultimately correct the findings after accounting for galactic dust. Science's self-correcting nature thrives on this diversity of perspectives, ensuring no single group's assumptions go unchallenged. Even the funding models reflect this unity. Projects like CMB S4, the next-generation observatory planned for the 1920s, are funded by a patchwork of national science foundations, private institutions, and international grants. The cost, often hundreds of millions, is shared across nations because the questions at stake belong to all of humanity. There's something poetic about nations that might disagree on earthly matters jointly investing in understanding the universe's birth. In an era of division, CMB research stands as a quiet testament to what we can achieve when we look beyond borders and work toward a common horizon, literally, the edge of the observable cosmos. The true power of these collaborations lies in their legacy. Every dataset released, every anomaly investigated, every theory refined becomes part of a global commons, accessible to a student in Kenya as easily as a professor in France. When the next breakthrough comes, perhaps the detection of primordial gravitational waves or a solution to dark energy's mystery, it won't belong to one team or nation. It'll belong to the species that dared to unite across every barrier to read the universe's oldest story together. The cosmic microwave background doesn't recognize borders, it blankets the Earth equally, a silent reminder that the universe's secrets belong to no single flag or institution. Yet as we pass its whispers into groundbreaking discoveries, thorny questions emerge. Who gets to own knowledge about the cosmos? Should a breakthrough in decoding dark energy be patented? Can a nation claim exclusive rights to telescopes studying this shared light? The CMB forces us to confront science's deepest ethical dilemma, the tension between open exploration and the realities of funding, competition, and geopolitical divides. History offers cautionary tales. When radio telescopes first detected the CMB's hiss in 1965, Bell Labs initially considered patenting the discovery before realizing its universal significance. Today, while raw data from missions like Planck is publicly archived, the tools to analyze it often reside behind paywalls or institutional barriers. A researcher in Nairobi might access the same microwave sky maps as one at Harvard, but without expensive software or supercomputing access, extracting insights becomes a privilege of wealth, not curiosity. This isn't just unfair, it's a cosmic irony. The universe's oldest light, free for all to observe, gets filtered through layers of human-made inequality before revealing its truths. The stakes are higher than academic fairness. CMB research isn't purely abstract. It drives technological advances with earthly applications. The ultra-sensitive detectors developed for telescopes like BICEP now enhance medical imaging and climate monitoring. Algorithms created to filter cosmic noise improve global communication networks. When such innovations emerge from publicly funded science but wind up patented by private entities, who truly benefits? Some argue intellectual property protections spur progress. Others see a betrayal of science's communal spirit. The CMB itself doesn't care, but humanity should. International collaborations offer hopeful models. Projects like the Simons Observatory pool resources across continents, ensuring data flows freely while crediting all contributors. Chile, host to major telescopes, negotiates guaranteed observation time for its scientists, a recognition that geography shouldn't dictate access. Even space agencies, often bound by national agendas, increasingly release CMB data worldwide within months. These efforts prove science thrives when treated as a commons, not a commodity. Yet challenges persist. Satellite launches require massive funding, often tied to political priorities. Groundbreaking papers still cluster around elite institutions, leaving brilliant minds elsewhere struggling for recognition. And as private companies enter cosmology, like startups mining CMB data for navigation technologies, the line between innovation and appropriation blurs. The CMB's light took 14 billion years to reach us. It'd be tragic if its lessons about unity got lost in terrestrial squabbles. Perhaps the answer lies in seeing the cosmic microwave background for what it truly is, humanity's collective inheritance. No one owns sunlight, no one can claim the stars. The CMB is no different, a gift from the universe to every curious mind, regardless of passport or pedigree. Protecting that spirit isn't just ethical, it's essential. Because the next revolutionary insight might come from a student in Lagos analyzing public data on a laptop, or a team in Kathmandu building homemade detectors. The universe speaks to all who listen. Our job is to ensure no one gets left out of the conversation. The cosmic microwave background isn't just a relic, it's the universe's oldest teacher, and we're only beginning to understand its lessons. Every flicker in that ancient light rewrites what we know about existence. From the invisible threads of dark matter weaving galaxies together to the eerie push of dark energy tearing space apart. This isn't just astronomy, it's a masterclass in humility. The CMB shows us a cosmos far stranger than anything we could have invented, where the rules of reality bend and twist in ways that still leave physicists wide-eyed. Think about what this means for us right now. That faint glow filling the sky isn't some abstract scientific curiosity. It's the reason you're here. Without those subtle temperature variations, gravity would have had nothing to sculpt, and the cosmic web that cradles our Milky Way might never have formed. The iron in your blood, the calcium in your bones, even the device you're using to watch this, all of it traces back to quantum fluctuations magnified by inflation and frozen into the CMB. You're not just observing the universe's history, you're walking proof of its story. And the wildest part, we're still at the beginning. Next-generation telescopes like CMB S4 will peer deeper into this light than ever, hunting for the faint swirls of primordial gravitational waves that could reveal inflation's energy scale. Imagine unlocking secrets from the universe's first trillionth of a second, a time span so short, it makes a blink look eternal. These aren't just technical triumphs, they're humanity reaching across time, using microwaves as a bridge to moments before time itself had meaning. But here's the real magic. This isn't a solo journey. Every viewer, every curious mind hitting like or sharing this video becomes part of the quest. Maybe you'll be the one spotting an anomaly in public CMB data, or inspiring a future physicist who cracks the dark energy puzzle. The universe didn't just give us a mystery, it gave us a shared mission, written in light older than stars. So stay curious. The next chapter of this cosmic detective story is yours to explore. Hit subscribe to join us as we unravel more wonders, and drop your wildest theories below. After all, the CMB's greatest lesson might be this: the universe loves a good plot twist, and we're all here to witness